Welcome to AOS2. So we are officially in the second area of study of VC Chemistry Unit 3. Okay, so today we'll kick off with rate of reaction. So we'll get introduced to collision theory in this session and try to understand from the point of view of collision of particles. And then we'll learn about how to qualitatively interpret the Maxwell-Boltzmann distribution curves. Then we'll revise a little bit of exothermic and endothermic reactions, mostly focusing on energy profile diagrams. And we will look at a reaction from both energy profile diagrams and the Maxwell-Boltzmann distribution curves. The last, we'll talk about the role of catalysts, especially with reference to creating an alternative reaction pathways and how to represent it in energy profile diagrams. Let's start. Okay. So first of all, when we say rate of reaction, can you pick out one of the 4 units that actually captures the rate of reaction? Well, here, that's the rate of reaction. Okay, so rate of reaction is defined as the change in concentration of a solution or change in amount when there isn't a solution of a species over a period of time. So your unit must have time to the power of -1. Okay, so it's all about what has happened within a short period of time or long period of time in that case. Okay, so collision theories and chemical reactions. So first of all, how do we understand a chemical reaction? Is that particles collide and rearrange to produce new particles. Okay? That means products of a reaction are the results of reactant particles bumping into each other. Okay. A human or a social analogy of that situation is that you are the result of your parents colliding into each other. So they have to meet in person before any chemistry, before a reaction happens, and before producing you. Okay. Well, since we're using that analogy, so we know that not all dates will lead to a marriage. Just like not all collisions will lead to a successful chemical reaction happening. Okay? So only effective collisions will result in reactions. So basically particles colliding to each other all the time. But for successful collisions to happen, it has 2 criteria. First of all, particles must collide with the correct orientation for old bonds to break to create new products. Secondly, they must collide with sufficient energy so as to break the old bonds with the reactants. Okay? Let's look at first criteria, correct orientation. Now, if these hydrogen iodide particles, these 2 particles, if they collide in that way, it's not efficient, it's not sufficient for all bonds to break, so the hydrogen iodide bonds to break, and therefore that is an unfavorable orientation. Okay? But if they actually collide head-to-head and toe-to-toe, now that is a favorable orientation and the reaction is likely. Okay. So then you'll be asking, okay, so how do we make sure all particles collide in a favorable orientation then? Because we want reaction to happen, right? Well, the sad news is that we can't do much about the orientation when the particles actually collide in the reaction. Another human analogy here is kind of like some people are born into liking guys, or other people are born into liking girls, or some people are born to like both. Okay? So in a social event, they must meet their favorable gender. So in particles, that will be favorable orientation, okay, for any chemistry to happen. And there really isn't much that we can do about it to change the orientation, the preference of people, okay? So you're born with it, there's nothing that we can do to change it. Just like we can't change how particles collide into each other. The orientation of particles colliding into each other. Well, energy, that's the second criteria. So when we talk about energy, we actually need to come back to revise the energy profile diagram for exothermic and endothermic reactions. Okay, so did you see on these two graphs? Okay, there are two energy represented. Okay, both graphs have a little bump here, and those bumps are what we call activation energy. Okay, so when we say particles must collide with sufficient energy, that means they must collide with the minimal amount of energy that is larger or equal to activation energy for a reaction to occur. Okay, so these two small bumps are the sufficient energy that particles must have for a reaction to go forward. Okay, so reactant particles must collide with larger or equal to activation energy to react. Otherwise, even if they still collide, they'll still collide, and they might still collide with correct orientation, but without sufficient energy, they will just rebound and simply move away from each other, even after they have collided into each other. Okay, so sufficient energy means larger or equal to activation energy. Now let's zoom into activation energy. So since reactant particles must conquer activation energy, like this, they must conquer that small mountain, okay? So then the size of the mountain, the size of activation energy, will determine how easily it is for a reaction to occur, okay? So another way to understand this is that particles actually do collide all the time, okay? But without the existence of activation energy to actually stop them from just spontaneously react, and the chance of successful collisions will increase immensely. So without this bump, many collisions would directly result in reactions, okay? So many reactions will spontaneously happen without a trigger. For example, as humans, we're basically made of hydrocarbons, okay? And we are bumping into oxygens in the air the whole time. So what is stopping us from bursting into flames right now is the existence of activation energy for this particular reaction. Without activation energy, we will literally burst into flames right now and produce carbon dioxide and water as a result. Now, so the activation energy is like a mountain to climb for reactants. So just imagine if the mountain is lowered. Then more reactant particles will be able to get through within a shorter period of time and therefore result in a faster reaction. Okay. So this is an example of a fast reaction, which is the reaction that we use to make bombs. Okay? So essentially, it is a decomposition of a substance called nitroglycerin, and it has a very small activation energy. So small activation energy will lead to more successful collisions within a short period of time. So when this reaction was first discovered, even a small bump will give the particles of the reactants enough kinetic energy to overcome that small EA and cause it to explode. Okay, basically an explosion just means a reaction happening really fast. Okay, so this reaction is much more powerful than conventional power. However, because the activation energy is too small for a longest period of time, we can't even use it because it's too dangerous until, well, Alfred Nobel found a way to stabilize it. Now, let's link collision theory with rate of reaction. Okay. Here we got to introduce Maxwell-Boltzmann Distribution Curve. We've been talking about energy and lowering activation energy to increase rate of reaction. How does it look like if we draw our diagram in this way? So this is a distribution of kinetic energy of reactant particles at a given temperature. So on the x-axis, okay, the horizontal one, we're representing energy. So when it goes towards the right-hand side, it has higher energy. And the y-axis gives you the number of particles with that particular energy. Okay. So we can see that at a given temperature, most of particles of reactants don't really have enough energy to cause a reaction. So they can bump into each other the whole time, but no reaction will happen. It's only a small proportion of the reactant particles have enough energy, that is, larger or equal to activation energy, to actually have a reaction. Now, so what can we do to change the rate of reaction? We talked about before, we can choose to lower activation energy. So how would it look like on this diagram, on this distribution curve? Well, we can see that our activation energy is here, and currently there's only a small proportion of particles with sufficient energy to react. What if we can lower the activation energy to here? Did you see that if we actually can lower the activation energy, then there's a larger proportion of particles with sufficient energy to react. All right. Now, so by lowering activation energy on this Maxwell-Boltzmann distribution curve, we can easily see we increase the proportion of particles with sufficient energy, and therefore we can increase the proportion of successful collisions. And this can be done by using a catalyst. Okay? So now let's look at from an energy profile diagram point of view. How does it look like when we add a catalyst to a reaction? So reactions with a catalyst have a much lower activation energy. So can you see that here? The old activation energy is that high, but once we added a catalyst, the activation energy is significantly lowered, and therefore making it easier for reactants to actually break bonds. Now, what if you're asked what's the effect of using a catalyst on rate of reaction? Here is your golden response for an exam. Okay. So catalysts reduce the activation energy by providing an new, or you can say an alternative reaction pathway to increase the proportion here of reactant particles with sufficient energy, and therefore increasing the proportion of successful collisions. Okay, so you can see that energy profile diagram gives us a view of alternative pathway created by using a catalyst, and then Maxwell-Boltzmann diagram gives us a clear view of increasing the proportion of successful collisions. Lastly, I have two questions to ask you. First of all, does catalyst change the enthalpy of the reaction? Well, we can't really read enthalpy from Maxwell-Boltzmann distribution curve. Okay, enthalpy can only be found on energy profile diagram, which is the one here. Okay, so has catalyst changed the enthalpy? Where is enthalpy on the diagram? It's here. Right? So you can see that catalyst has lowered the activation energy, but it has done nothing to change the energy difference between reactants and products. So no, catalyst will not change the enthalpy of a reaction. Okay? Secondly, does catalyst get consumed in the reaction? Well, the answer is no. Catalyst does not participate in the reaction. It creates a new pathway. The pathway is there. The pathway is not participating in the reaction.